Welcome everybody to the disputation of Pedro Pablo Lucas Bravo. My name is Özge Alay and I will serve as the administrative committee member for the education committee. And we have Professor Stefania Serafin from Copenhagen Hearing and Balance Center, Copenhagen, as first opponent, and Associate Professor Kıvanç Tatar, Chalmers University of Technology, Sweden, as the second opponent. Pedro will defend his thesis titled Human-Swarm Interaction Music Systems, Exploring Collaborative Sonic Creation Between Humans and Autonomous Agents, for the degree of Philosophy Doctor, in the afternoon at 1:50. But first, he will basically present his work as part of the trial lecture on the topic of sound synthesis and sonic interaction in VR and XR. Pedro, the floor is yours.
Thank you. Okay, welcome everyone. So today's lecture is entitled, as you hear, Sound Synthesis and Sonic Interaction in Virtual Reality and Extended Reality. Okay, so this topic could have different approaches, but I will focus mostly on concepts regarding this topic, and also I will adopt a design perspective to have the initial insights to create immersive sonic interactive experiences. So we start with the concepts. We will take a deep look in some of these components. So one is VR and XR, virtual reality and extended reality. So we have the common understanding in industry, the consumers, or even research about what is XR, extended reality. So it covers virtual reality, augmented reality, and mixed reality. So we have these three terms. Extended reality can be seen as, the word said, an extension of the physical world, the reality, with a digital world, and that occurs in several levels. So one level is virtual reality, in which you are totally covered by a virtual environment. So you can have some interactions, physical interactions, because you are still aware of your body into this virtual world. And usually you reach this with the famous VR headsets. So then we have augmented reality that traditionally or historically is something that you superimpose, a virtual object that you superimpose into the reality. And you can manage this with smartphones or like tablets, so you probably have experienced this before. And then we have mixed reality that in some sense, and even lately, also can be seen as augmented reality because you still are mixing physical elements with virtual elements. But this one also, as virtual reality, can be reached with headsets. So I will give you examples of each one. This is for virtual reality. For the traditional concept of augmented reality, this is from an AR artist. And in mixed reality, this is an example of a multiplayer experience of badminton. It's a more immersive and embodied experience where multiple users interact with the same virtual object, which is the ball. We will see this. Okay. But to be more precise, we can frame this concept in a framework that is called the reality-virtuality continuum. So this is a theoretical framework that describes a continuous range from the real environment to the virtual environment. And in the middle, we have mixed reality. So actually, we can frame all what I showed into this continuum. Like we have in the left part augmented reality, in this part something that is called augmented virtuality, which is not much common, and virtual reality in the far right. So just for explaining this part a bit, the augmented virtuality will be if you are in virtual reality, total covered, but you still can have, like for example, videos or snips from the physical world. And then we can position our examples here. So basically here we have virtual reality, and this example of augmented reality will be in this part. And mixed reality, as we understand it, is sort of a mix, kind of in between of this, in the middle of this continuum. Yeah. So this lecture focus more in this part, in this right part, that is about MR and VR, because these experiences can reach it with this device, the head-mounted display. So I will talk about that later. Then we continue with sonic interaction. So what is sonic interaction? We can define sonic interaction as the use of sound to convey information, meaning aesthetic and emotional qualities in interactive concepts. So if we follow the anatomy of a sonic interaction, we start with a motor behavior, with an action, and we apply this to some sort of mechanical system, to a sound-generating object. Then we will have some acoustical information that goes to our ears, but also we have additional information from our bodies, from the motor behavior or the action, and from the sound-generating object. That could be kinesthetic, tactile, and visual information. Then all this information is processed as sensation, perception, and cognition, and this can come back to the motor behavior. So this is a loop, action-perception loop, in which we can continuously, if we want, doing this sonic interaction. So then the field that covers this is called sonic interaction design, which is an interdisciplinary field. It spans computer science, engineering, acoustics, psychology, design, humanities, and many others, in terms of research and practice that explore these sonic interactions. So sonic interaction design explores these questions about embodiment, performance, also investigate how sonic gestures can convey emotions and promote expressive and creative experience. And I want to highlight this word because this is very important for the lecture, the experience. So experience can be framed in the famous third wave of human-computer interaction, in which we are not looking just into function or efficiency. It's not just like a tactile testing, okay, it works and it's efficient in a relative good time, but also we want to provide some experience. So we have to think more about that. Even a really simple sonic interaction, like pressing a button, can be a whole experience, and I will show that next. So we have these two examples, one from the experience of pushing a button. We can hear it. So as you saw, only with the action of pressing a button, you can have very different experiences depending on the context. And then we have something more complex, which many of you are familiar with, the NIMEs, the new interfaces for musical expression. And then we have a huge range of possibilities for sonic interactions. So I give you some examples. Yes. But our context is in virtual environments. So with virtual environments, we mean the immersive media. So what we saw before, the extended reality point. We cover VR, AR, MR. So I'll give you two examples about this, one in virtual reality. Okay. And then I have one example in mixed reality. So here I want you to put attention in all the elements that you can have here, the several interactions, the interfaces that are there, and how can you also use the physics properties of the world into some objects. Okay, so that's something that we actually want to achieve when we want to design and implement these experiences. But what about the sounds that are produced in such virtual environments? So then we enter to this other part, which is sound synthesis. But before, we need to be aware of something fundamental. Let's consider one of the building blocks for sonic interactions, which are the sound sources. So the sound sources are the commonly sources or in the physical elements that are capable of producing sound. But for our scope, we will use the digital part. So how can we reproduce the sounds digitally? Because that's that we are interested in for virtual environments or immersive environments. So first, we can adopt two paradigms here. One is the sound as a data or the sound as a process. So the sound as a data is a sample-based approach, and the sound as a process is a synthetic-based approach. So we'll have some comparison between those two. So the sound as a data are basically the pre-recorded audio assets. So the audio files, the .wav, the AIF, the MP3, the ones that we can use for triggering some particular actions and sonify it in a discrete way. And the synthetic-based approach is based on runtime creation. So we create the sound at the moment. So it's not pre-recorded, and it's real-time. It uses real-time models for doing this. So the sound as data approach, in here we have assets that are fixed in time. So we know what is the duration of this asset. But in this other approach, this is variable in time. Even can be infinitive. That depends on how long we want to reproduce these sounds. And in this approach, we can have a perspective or event-driven perspective. That means that we will have discrete events that we can sonify, that we know in a way beforehand. And the sound as a process is a procedural approach. So we can have continuous motion here. It doesn't matter how long is this, and we can provide this. In terms of computational load, so this sample-based approach uses higher memory because we have to load the data into the memory for having a fast retrieval, but it uses a low CPU, low processing. But in the case of the sound as a process approach, we use low memory because we actually, or usually, we don't have data or heavy data load in memory, but we need to use more CPU because we need to use these models for the real-time process. So I will give you two examples of this. One is from a AAA game, and I want you to hear the environments and the sounds that are happening here. It's very short. Okay, so what is happening here? So this is a video game, right? And we usually use game engines for also VR or XR experiences. And we have these pre-recorded audio assets that we want to reproduce into the virtual world, right? So we can do it directly into the game engine with programming, but sometimes the designer uses a software called an audio middleware that allows them to have a more friendly interaction for integrating these sounds. Then we have an audio engine with, inside the global engine. And the thing is that we can have post-processing effects. So even though that this is fixed, we can do, for example, going volume up or down depending on what is happening, doing some pitch stretching or any other process. But there are always trade-offs in doing that. And then we have the output. So that is how it works. For the synthetic approach, I have this example. You can hear it. Okay, so in this case, there is no pre-recorded file playing back, but a real-time and continuous single sound over the music, which is a sine wave. The pitch is modifying while the avatar is going from one side to the other. That's the advantage of synthetic sound, that we can be more flexible in continuous interaction. Then we can now talk about sound synthesis because it's approach into this. But we can talk first about synthesis. What is synthesis? We can say that it's a process of bringing together and making a whole. But this doesn't imply just a random assembly. It's something that you can be creative with. And regarding sound synthesis, we can say that it's the process of producing sound, and it can reuse existing sounds by processing them, or it can be generated electronically or mechanically. So here, for our interest, we focus in the electronic generation of sounds, but particularly for digital sounds. So you can see this process as an element that is called the synthesizer, and in terms of software, it can be an audio procedure. Then we have several parameters that we can modify to produce a sound output. So sound synthesis, I mean, there are several classifications of this, but one that I found that can resonate is this one. So we can classify for producing sound synthetically in signal models, physical models, and data-driven models. So a signal model uses abstract mathematical structures for the sound generation. And we have several techniques here. For example, subtractive synthesis, in which you have a generator and then you have some process of filtering for getting the sound. I have an example of this. Then we have additive synthesis, in which we use several sine waves. We join all together for making a sound. So we can have something like this. Oh. Yeah, sorry, that's an issue with the audio system of the room. Yeah, but we can go to the next. And frequency modulation is where when the frequency of a sound signal can be varied with the amplitude of another signal. So I hope this plays back. Yeah. And then we have granular synthesis, in which samples or pre-recorded samples are reduced into tiny, overlapping acoustic events that we call grains. And then we put everything together in many different ways. So this is an example. Okay. And then we have the physical models, which use analytical descriptions of the mechanical and acoustic behaviors of the real world instruments or objects. So one technique is model synthesis. So model synthesis identify natural resonant frequencies that are called modes of vibration. So it tries to replicate a structure in several or parallel filters. So it's a little bit complex, but that's how it works. And then we have an example here. So as you can see, there are virtual objects. And through model synthesis, we can reach a similar sounding as real objects. Then we have this technique, data-driven models that are based on machine learning, deep learning, or database approaches. So this is an example, the RAVE model, which stands for Real-Time Audio Variational Autoencoder. This is from IRCAN. So it sounds like this. Yeah. Okay. So in the context of virtual environments, usually we see sound synthesis with this name, procedural audio. So we can go back again to our diagram. And basically, procedural audio means that we have a procedure, something in which we are going to process these streams of data regarding the audio using any of the techniques that I showed before. And we can modify in real time, again, these parameters to produce a sound output. Yeah. But for the contextualization of this in virtual environments, we have this way for designing procedural audio. So basically, we can think about in two things, the model and the methods. So the model is what we want to create. And for establishing the model, what we can do is think about the objects or the targets of interaction. We can do a physical analysis of these elements, but also we can do an audio analysis for building this model. And then we can have behaviors, parameters, structures, specific structures of these models, or several streams of audio for composing this model. So then when we have this model, we can apply methods. So the methods are how do we create what we can have, or the idea that we can have with this model. So in this case, we can use the synthesis techniques with a palette of synthesis synthesis approaches, as I showed you before. And then we can have synthesis parameters that control these techniques that can be mapped also with the parameters of the model that we want to design. And when we have all of this, we can have an implementation plan for this. And as you can see, it can take ideas from the real world, but we don't have to be limited to that. So we can use inspiration from the real world for other objects or other kind of interactions that can be part of a fantasy world. So at the end, procedural audio should support continuous and adaptive sound sources. Okay, now that we know all of these components, we are going to extract some insights for a really important question that we need to ask to ourselves. So we know that sound synthesis can produce continuous and adaptive sound sources. PR and XR provide us immersive environments. And sonic interaction is the experience that we want to deliver. And I highlight again this experience because it's the one thing that we want to focus on. So considering this, we can ponder this question. How do we design and implement a continuous and adaptive sonic interactive experience in an immersive environment? So next we're going to see what we mean with design and implement this experience. So in terms of design, we have to think about how can we deliver the experience regardless of the implementation. So here, you don't think much in the VR headset or any of these things. You can even imagine that you can create things out of nothing. But you have to think how you can create that. So that's the design. And this is a top-down approach. That means that we start for some global elements, and then we go to the specifics of this process of design. And for this, we have 3 pillars: the body, the environment, and the objects. So for the body, we need to provide a sense of embodiment. So a sense of embodiment is concerned with a relationship between the oneself and one's body. And you can provide that into the avatar or augmentations that you can have in your body. And then you can ask the question, who am I in this space? And trying to lead the design with that question in terms of your body. And for the environment, we have an important concept that is called the sense of presence. That refers to the relationship between the oneself and the environment. And we have this concept of place illusion, which is the quality of having sensations of being in a real place. So you need to believe that we are there. Even though that this is not actual physical world, it's a fantasy world, you have to provide this belief to the users. And you ask, where am I? And then in objects, we have the sense of agency. So is this the sense of having control in relation to one's own body towards the objects? So here, play a concept called plausibility illusion, which determines the overall credibility of the virtual environment that concerns subjective expectations. And then you can ask, what can I do here? And what is real? And these pillars can be framed in these 2 components: functional qualities and hedonic qualities. So functional refers to the function that the sound serves for the user. It's how the thing should work. And then the hedonic qualities is the look and feel. It focuses in concrete sensory, emotional, and aesthetic experiences. So basically, we have to make this work, and then we have to embellish it, right? And then I will cover some design insights about each of these components. For the body, we can talk about, in terms of functional qualities, that we have to establish an unbroken perception action loop. We have to keep it there. And for reaching that, the sounds should reflect the user's physical effort and motor behavior. So we have to be congruent with what we are doing. So also, the body should locate sounds in a space. And spatial audio takes place here. So if something is sounding in one part of the room, so we have to be congruent with that. So we have to hear it in that direction. In terms of hedonic qualities, we have to provide a feeling of body ownership. We have to feel that this is our body in the virtual world. We have to synchronize the sounds with micro movements if you want to provide more credibility. Like, for example, if you rub your hands, so probably you can reinforce that experience with the sound in the virtual environment. And we also can provide this that is called audio haptic cross-modal illusions. So basically, you can alter the user's perception of their own biological body. So one simple example could be if you want to be the superhero Spider-Man, right? And you want to give this experience. Something that you can do is like providing visuals in your hand for this net coming out and also the sounds. Then you have this experience as part of your body. Okay. For the environment, we have to provide room acoustics. So part of the illusion that we want to provide here is like we have to be congruent with the environment. Even though this is, again, a fantasy world, you have to believe that you are there, and you can approach this with room acoustic, like, for example, reverberations and that kind of things. You can also provide sound attenuation. If you are approaching to some part of the environment, you can have the volume of the environment increasing or decreasing depending on the distance. So that's a functional thing. And if you are in shared spaces, if you are with other users, so it could be the case that you don't need to hear everything, so you need to build, or you need to think about what is your personal space and what is your shared space. So depending on that, you can design the sounds that are in there. In the sense of hedonic qualities, we have to reinforce the emotional tone. So we can reach this with music, but also with the timbre of the sounds. So that could evoke some emotions for you. We have to provide intimacy. How can we connect with the objects, with the sounds? Well, in this case, it's the environment, with the environment for being into the place. And then we can create also this listener envelopment sensation. It's the sense of being surrounded by the reverberant sound field. So you can frame this or reinforce this with the room acoustic that we provide, but we can add more things to reach this. Like, for example, we can complement the environment with other objects that can give the experience into the simulation, that the experience that you want to deliver, right? Good. And then we have the objects. So the objects are the target of actions. So we have to provide evidence of reality, which can be event-based or continuous interaction-based. So then we can think about what I talked before, the balance between using the approach of the sample-based approach or the syntactic-based approach. If we need to just trigger sounds depending on the actions, we can just use sample-based. We can use also synthesized-based, but that depends also of the balance of this. And we can explore synthesis with continuous interaction in this case. And with reality, I put in quotes, because again, depending on your design, the reality would mean the reality that is happening in that world. Okay. And we can also transmit or convey physical properties or magic interactions. So if an object logically has to sound in some way, we can model the sound for reinforcing that way. You can use modal synthesis in this case, for example. But if you want to imagine something more out of the box, so you can think in the famous magic interactions, and you can think beyond in the qualities that are part of this magic interaction, the fantastic worlds that you can imagine, and try to combine maybe metaphors from the physical world into a new world. And again, here you have to be congruent with the space. Again, spatial audio. So the objects can be in any place, and you have to hear it in that direction. For hedonic qualities, we need to provide an emotional identity. So in some way, you have to connect with the object, depending on the experience. We can also afford virtuosity. So it could fit better for musical instruments if you have some affordances of the instrument, but not necessarily. You can have an object that can have some qualities, and you can use it in several ways. You can provide interesting affordances to that. And then we have to balance magic and function. So this is very important, because if an object is intended to doing something, and we want to embellish or we want to provide something to evoke some sort of emotion or a specific experience, we have to see if what we are adding are affecting the general experience, right? So we have to balance that, magic and function. And then something that might contradict this part is bend the special rules if needed. So again, you might hear something in some part of the rooms, right? But what about if you want to provide a sort of, I don't know, crazy experience? So you might play with a special sounding of an object. You are seeing something there, but you are listening in another part. So that depends on what you are designing. You can bend these special rules. Okay. So after this, uh, we know, in a way, how to design these sonic experiences. And then we need to think about the implementation. So then we go into the reality, and we see, okay, um, for doing this, maybe I cannot use this technology or this other technology. And then you start to frame in all the possibilities that you can use for actually implementing your design. And the implementation is a bottom-up approach. That means that we are looking at the specifics, the things that we need, like, for example, the sound synthesis techniques, if we need sample-based approaches, or any other kind of technique. And then also we can refine the design to fit into the possibilities that we might have. And mainly, in implementation, we think about the technology. So we have the hardware and the software. And in the hardware, we use mostly the head-mounted display. This is the MetaQuest 3. And in software, we usually use game engines. And the most famous ones are Unity and Unreal Engine. But particularly for sound, in the display, there is like a built-in speaker, which provides you binaural rendering. So in that sense, you can have a spatial audio into the headset. So this is the headset. This is a MetaQuest 3. And here, you have these little speakers that allows you to hear or to experience a spatial audio. In terms of software, apart from the game engines, you might need something else if you are not much skillful in programming, which are called the middlewares, like Fmod or WWise. So basically, you can design the virtual environment there without much going into programming. So you, as a sound designer, you can use this software to create the experience. But additionally, you can expand this hardware into something more complicated. You can add a spatial audio system with a multi-speaker system. So then you can have, apart from the sounds that comes from the built-in speakers here, you can be surrounded by other speakers and, in a way, improve the immersiveness of the environment. But for this, you might need additional software. Sound engines like Csound, Pure Data, Max MSP, SuperCollider, there are others. But still, you need to use additional computational power. You might need to use additional computers, and that would require networking. So this is a very complicated setup that you can achieve, but it's possible. But what if we don't want to have all of this and we want to be more portable? We want to come back to this shape. So one thing is that usually in games, as I explained before, they mostly use sample-based approach. And because of this, several of the tools for developing this, they don't support an easy way to implement sound synthesis. But lately, we have something better. I will explain that later. In that sense, you might need to have this complicated setup of having another computer, having another software running and trying to synchronize with the headset. But we need this experience to be built in. And especially if we are going to use sound synthesis, we have to think about how we can overcome this issue. So the question is, how can we make use of built-in sound synthesis in this device? In terms of these two game engines, Unreal Engine has a really good tool called MetaSounds. So you basically have a visual programming language. It's a built-in tool in which you can create your sounds and apply all the synthesis techniques that I was talking before. That's an option, but for Unity, the Unity game engine, which is like engine widely used in game development and also in immersive environments, you need to program here. So you need to know digital signal processing and do something with the buffer, the audio buffer, to create some procedural audio. But fortunately, we have tools, wrappers, for depending of the device or depending of the hardware and software situation. But particularly for this device, for the MetaQuest 3, there are two that works, C-Sound and Choc. So there is a wrapper called C-Sound Unity that you can use for implementing this built-in into the device. Or you can also use this plugin Unity for having this. And you don't need to have all of these implementations. But of course, if you have the skills and the ability to do this, you can also switch between those two. Okay? So to summarize this, we have the design and implementation. In the design, we have functional qualities and hedonic qualities. And it has to do with the three pillars that we talked before: the body, the environment, and the objects. Then we have the implementation. We talk about hardware and software. In hardware, we have headsets, VR, XR headsets. We can complement this with speakers, or we also can use additional computers for having a whole setup, as I showed before. And in terms of software, we have game engines like Unity and Unreal. And we have middlewares like Fmod, BWise, or audio engines like Pure Data, MaxMSP, C-Sound, Super Collider, or any other. So as you can see here, this is just one of many frameworks that can be used for building immersive sonic experiences. So, but we can always combine other paradigms and design principles, and specifically the ones that concern with sound and music interactions. So if we look in the literature, we will have a lot of frameworks, design recommendations, and specific things that we can use for these sort of systems. But the point is knowing part of what is out there here in this presentation and start to create such exciting sonic experiences. So I invite you to explore more, to take this as a first part of how can we design this, and looking at the technology, looking at the techniques that is out there, looking at the paradigms that we have for design, because one reinforces to the other. You can start even explore, not even from the design point of view, you can even start exploring from the technology. So what the technology is affording to us. So in that sense, you can even have a back and forth between design and technology for doing all of these implementations. And something very important that you can keep in mind is that you have your own intuitions, right? So you can think about something and then you can put that against a framework or against any other thing, but still it's your idea, right? So it's an experience that you want to deliver. You can try it you first and then try it with others. But again, this is one part that you can use. And I hope that this is useful for your next amazing sonic interactions. Thank you very much.
Thank you, Pedro. I now turn to the committee members. Do you have any questions?
Questions?
Thank you. Thank you very much for your excellent presentation. I really like also that you use the rhythm of colors in your slides. Very nice.
Yeah. Nice.
I was curious. So what do you think? So Unity is a very big company with a very big sound team.
Yeah.
Why do you think they don't have a good sound engine yet?
That's a good question. I mean, I don't know how big is the audio thing, and I have seen in forums like many people like saying, okay, we need sound synthesis, we need this, we need this. Unreal have meta sounds, so yeah, but they have. You can see in the forums someone probably asking in general from the company saying, yeah, we have these priorities, we have to fix this in the rendering pipeline and fix this. So, and one thing that probably I didn't mention is like sometimes in these companies or in general in these experiences, the audio is pushing a little bit out. So, but I mean, they have to also be aware that the audio is part of the experience. Otherwise, we cannot complement the experience. So I guess it's more like bureaucratic thing and the order of priorities that they have in the companies. Yeah.
And yeah, just a follow-up question. What about Meta? Because Meta also has many nice SDKs, for example, for haptics, but there's not really one for sound either. And they have an even bigger team than Unity.
Yeah.
So
Yeah, in terms of, I haven't explored that deeply into the technology or the built-in technologies of Meta because for the work that I'm doing, I'm using Unity. So I'm not sure if they, because I think I saw something related to that, how far they have been with that. But the problem is that they might have this, for example, the spatializers and everything for the sound, for the gain engines. But as far as I know, they don't provide synthesis. But maybe if I have a look, they might have something now. I'm not sure if there is something.
I don't think so. So now they are like even deprioritizing. So I was just curious if you know, but because it's a shame. I mean, but thank you very much again. It was really excellent.
Okay, cool.
Thank you, Pedro. That was great, and it was quite thorough. It was awesome to learn from. I learned some things from this. To be honest, I'm not super familiar with the, specifically the sound synthesis literature for XR and VR. I wonder, where does this hedonic qualities term, does it come from the literature or is it something that you proposed?
Yeah, it's like, it's a merge. Yeah. So because like, if you look at this topic, it could be very overwhelming. You can approach it as different ways. But from the work that I did in my PhD, there is some papers that try to frame the design into these elemental points of functional and hedonic qualities. So from the material that I was looking at, I said, okay, maybe I can frame the design into a framework that involves these two. And as an overall perspective of how can you start designing this. So it's basically a merge that I found in a perspective in human-computer interaction and bringing into this. Yeah, it's not tested, so it could be something that future research, but I just ventured to propose that, sort of.
Great. One thing that I noticed perhaps as a comment is, in this framework, it's very individual human interacting sort of setup, that maybe there's more there about the multi-user cases when you go into communities and what happens there. Like one of my memorable experiences that I did a trip with 8 of my friends in Valheim, and that was one of the most memorable things that I've done, and the sound is part of it. So I was wondering, like, how, because your thesis is also about multi-agent systems, right? So you are talking about multiple agents interacting with each other in an immersive environment. So maybe that part is also a little bit to given thought about, what could be more interesting things there.
The talk, I mean, if I have to go more into specifics, it's like maybe focus in the experience of one person in a way. Of course, you have to take into account if you are into multiplayer environment. In my thesis, it's also like a one only person, but you have multiple agents, right? But for multiple people, a multi-user experience, there are more things to consider. And this is a limitation of this talk, I would say. This is approach to the experience of one user. That, of course, can serve for a multi-user experience, but there are other things that you have to take into account. Yeah.
Thank you.
Okay, thank you very much. I think we can conclude the trial lecture and we will resume at 1:15 with the PhD defense. Thank you.
Okay, thanks.
Okay. Distinguished members of the committee, dear colleagues, ladies and gentlemen. My name is Kai Olav Ellefsen, and I'm an associate professor at the Department of Informatics, University of Oslo. As the appointed moderator, or custos, it is a pleasure to welcome you all to the disputation on a dissertation submitted for the degree of PhD at the Faculty of Mathematics and Natural Sciences at the University of Oslo. The faculty's PhD program council granted Pedro Pablo Lucas Bravo application for the admission to the PhD program on the 25th of March 2024. On the 5th of March 2026, Pedro Pablo Lucas Bravo submitted his dissertation entitled Human Swarm Interactive Music Systems. The supervisors for this work were Professor Kyrre Glette, Department of Informatics, University of Oslo, postdoctoral fellow Alexander Sorkovsky, Similar Research Laboratory, Professor Stefano Fassiani, Department of Musicology, University of Oslo, Norway. On the recommendation of the Department of Informatics, the faculty appointed the following adjudicating committee. Professor Stefania Serafin, Copenhagen Hearing and Balance Center, Rikshospitalet Copenhagen. Associate Professor Kivanch Tatar, Chalmers University of Technology, Sweden. And Professor Özgü Mira Alay Erduran, University of Oslo, Norway. The adjudicating committee reported on the 24th of April 2026 that it had found the dissertation worthy of being defended for the degree of Philosophiae Doctor. The candidate presented the required trial lecture on a prescribed subject entitled Sound Synthesis and Sonic Interaction in VR and XR. The adjudicating committee has found the lecture satisfactory. During the disputation, Professor Stefania Serafin will act as first opponent, and Associate Professor Kivanch Tatar will act as second opponent. First, the candidate will give us a brief survey of the purpose of the work and the results of the investigations. Then, Professor Stefania Serafin will put the work into an international context and present her opinion on the dissertation. Afterwards, Associate Professor Kivanch Tatar will continue the opposition. The candidate will be allowed to answer the comments or questions from the opponents. Finally, it will be possible to speak ex auditorio. I now call on Pedro Pablo Lucas Bravo to present his scientific work.
Okay. Thank you very much. Welcome, everyone. Thanks again for coming here. The title of my dissertation is Human Swarm Interactive Music Systems, exploring collaborative sonic creation between humans and autonomous agents. So this work started with a simple idea. Let's make music with a swarm. What that means. So it comes from the inspiration in nature. We can find swarms in nature, for example, birds, ants, or insects like the fireflies. They are simple organisms, but when they interact together in a way, you can have complex patterns emerging. And these behaviors can be framed into something that we call swarm intelligence. So from swarm intelligence, we can have inspiration from artificial systems. And one of these systems are, or these several systems are the ones that I developed for this dissertation. So I will show you an example of two systems that were evaluated in this thesis. Okay, so this presentation is a summary of the journey from the inspiration based on nature that you just saw to the systems that you just watched. So this is the content of the presentation, and we are starting with a little bit of the background. Story intelligence, what is this? So we can define story intelligence as an emergent collective intelligence of groups of simple agents, which is typically based on a social metaphor of simple living organisms, like the insects or birds that you saw before. So these agents interact locally with each other and their environment following simple rules, resulting in a decentralized, self-organized behavior. So if we want to introduce a human in an artificial system that is based in this context, we look at this field, human-swarm interaction, which is actually a field from robotics. So from the literature, we have this diagram that tells us how a human can interact with a swarm of robots. So we have an operator, and we have the robot swarms, and in the middle, we have a way to interface this interaction. This is done through a communication stage, but basically in this research, we consider the control methods. So control methods for swarm interaction are two: group control and individual control. So group control means that we can control the whole swarm at once. Like for example, if I have an interface and I want to move the whole swarm from one point to the other, I just have to move the point, right? And all the agents in the swarm will obey and will go to that point. Individual interactions are the interactions that you can exert in one specific agent or a subgroup of these agents. So in that sense, when you have these changes, that can influence the other agents in the group. So one gap that was identified here was the limited interaction at the level of individual agents. Especially for swarm robotics, if you want to interact individually, and especially in a body way, it can be complicated. Like for example, you cannot touch a drone while it's flying, right? But these interactions at individual level can be helpful for interactive systems, more specifically music systems. So then we have this human swarm interactive music systems. We can define these systems as an improvisational system that allows users to interact with a swarm of self-organized artificial agents that exhibit emergence in a sound and music context. So we have three types of platforms in which we can implement these systems: virtual, virtual, and physical. So in virtual systems, we have agents that are totally virtual. We can have an environment that is in a 2D screen, and the way to interact are like, for example, physical interface or probably gestures or other kind of interface with this 2D screen. Physical virtual are the systems that use immersed technology, like extended reality or spatial audio. And physical systems are the ones that are robotic systems. So we can actually interact directly with physical elements. So the gaps that were identified here were these three. There was a low level of embodiment. That means that mostly these systems are focused in a virtual environment. So there is a limited capacity to interact directly with these agents in an embodied way, which is not that much the case if we look at to physical or physical virtual. But the problem with physical, as I mentioned before, is that you sometimes cannot touch the agents, right? And this one could be more fitable for this purpose. Then we have the lack of standardized technological platforms. So we have out there from the robotic field several platforms that can help to develop multi-agent systems, but there are no particular platforms that include built-in sound synthesis or sound capabilities for implementing music systems or sound systems regarding multi-agent systems. And then we have this gap, the need for deeper evaluation of human operators in musical settings. Even though in the field of human-swarm interaction, we have some studies that cover this, we don't have much regarding systems in musical settings. So to approach these gaps, this research has as objective design and implement music systems based on autonomous agents that interact with both other agents and human users, as well as understanding emergent properties from the systems and from humans engaging with them. So to approach this objective, there are three research questions. One regarding algorithms. How can bio-inspired algorithms be used to promote music creation and interaction with a human in such musical context? Second question regarding the systems. Building up from these algorithms, how should one design, implement, and evaluate human-swarm interactive music systems? And the final question is regarding user interaction. How do users engage with human-swarm music systems during the exploration of a collaborative music performance? So to address these research questions, this dissertation is composed of 8 papers that overlaps in the solution of such questions. Okay, so I will talk a bit about the methodology and the results. So in the methodology, we have several components here. Everything encompasses literature review. Then we have a research and development framework that covers also algorithm development. We have system development, and we have evaluation from the system point of view and from the human point of view. So let's start with this one. This research and development framework is proposed in paper 1. It covers 4 dimensions: design, algorithms, technologies, and evaluation. In terms of design, one previous architecture proposed in the literature called the PQF architecture was slightly modified, just added this module to implement such human-swarm systems. So basically, you have a performer that is interacting with the environment. You have a P module, which is a module that catch the input from the environment. You have the swarm algorithm that needs some sort of knowledge. It could be very simple or it could be complex. And then the outputs are synthesized through a Q module into the environment. It could be sounds or also visuals, depending on the system. And then it frameworks propose also algorithms in all these stages, the technologies that can be used, like virtual physical and virtual technologies, and the evaluations methods that can be applied to this, ranging from quantitative and qualitative methodologies. Then we have the interactive systems. But for entering to the interactive systems, this work first based in 2 autonomous algorithms. So the first algorithm, called swarmulator, it comes from this term that combines these 2 words, swarm and oscillator. This model was proposed by O'Keefe and colleagues in 2017, and it refers to agents that exhibit coupled phase and spatial dynamics. So this is an example of how, when you have all these dynamics, can emerge complex patterns. And these complex patterns can be classified in several states, like this one. Okay, so to reach these states, you need to modify parameters that are defined in the model of this swarmulator strategy. So as you hear, this dynamic was sonified, and this is the result of this sonification. The second algorithm, that was a full novel algorithm proposed in paper 4, is a self-assembly algorithm. So this is based on the self-assembly approach, which is a natural growth process that involves local interaction rules to form patterns or structures without human intervention. So in this case, for this paper, there were sonic and music rules that were implemented in the dynamics of this algorithm, and the result of this is generative music that sounds like this. Okay, so those two, as you saw, is the autonomous behavior. But we want to include user interactivity to this. We went from autonomous to user interactive. So the interactive formulator system, again in paper 2, use these two paradigms of control, group control and individual control. So in group control, there are interfaces that changes the parameter from the model of the formulators, and for the individual control, a different agent was proposed, an interactive formulator. That means that this special agent can obey only to the user, so you can change the position and the internal properties, but this is not influenced by the other agents, but this influences actually the other agents. So in a way, you have an indirect manipulation of the swarm. This is a small example in a virtual environment for this system. Okay, the second interactive system, based on the self-assembly algorithm, was studied in paper 5. For user interaction, again, for group control, there was an interface modifying some parameters of the model. And for individual control, we provide direct manipulations. How did we provide that? Using extended reality. So this is an example of how it works. Okay, apart from that, there was a third system that actually was based in the other ones. So this human swarm AMS platform proposed in paper 7 is a system that serves to address this lack of standardized platforms for multi-agent systems. And basically, the architecture use an external controller, so you can use whatever programming language that you want, and you can control the swarm dynamics and sound and music properties from the system. And this is the whole architecture for this system. This is an example of this platform using Python as external controller, and this is a custom multi-agent musical system. Good. Then we enter to the two types of evaluations that we perform with the systems. The one is the system-centered evaluation, in which we approach emergent properties and computational performance. So in terms of emergent properties for the swarmulator, one example of this is the discovery of how a whole swarm can be influenced by this individual behavior. Like for example, here we have this interactive swarmulator, and because everything is mapped with sound, we can analyze, or we can check in the spectrogram how all the swarm behaves regarding this one. And as you can see here, we start with different frequencies that are represented by the colors, and they synchronize to one only frequency, trying to follow the state of this interactive swarmulator. So as you can see here, this conversion to this state is slow and in a non-linear fashion. Then for this algorithm, the self-assembly, this is one example of the emergent properties. We discover a quasi-regular patterns of assembly and disassembly. So basically in this algorithm, depending on some parameters, the agents assemble, and after some time they disassemble. And then we also check the spectrogram to see how this composition, according to the mapping that we propose in the paper, is affecting the overall sound output. Then we have computational performance, and in this case, there was a paper that investigate the sound engines that we can use for extended reality in the MetaQuest 3. So it has to do a bit with the trial lecture, and actually it contributes to the field of sonic interaction because it figured out that for this particular headset, between these two plugins, this sound unity is better and more efficient for this device, the MetaQuest 3, again. And according to these results, the system were implemented built-in, sound synthesis built-in, using this plugin. We also study computational performance in the artifact, in this research artifact that we proposed, the Human Sound IMS platform, and taking into consideration the frame time of the real-time processing. So we evaluate the external controller in Python, and we reach some numbers here. The problem is that, of course, this is tied to the hardware, but the methodology is useful for someone else to have this assessment into the system. Yep, and then we have the human-centered evaluation. So we now put a human there to interact. And one methodology that was used at first was autoethnography. Basically, the designer, the implementer of the systems, in this case, it was me, tried to figure out affordances, try to look for strategies in which you can have some sort of music performance or sonic interaction into the systems. So for paper 2, regarding formulators, this was done in a sort of music performance through a reflexive approach. Some of the results include the identification of the asynchronous rhythm that were happening there, some variations in musical patterns when you change the number of agents, and how these interactive formulators can influence the swarm in this music performance. In paper 5, we also use this approach of autoethnography, but we use two methods, quantitative and qualitative. In quantitative, we record real-time data from the headset, and in qualitative was also, like the previous paper, a reflexive approach. And we also compare how the interactions from the user shapes the autonomy of a system. Like, for example, I showed before these quasi-regular patterns, and then you have someone interacting with the system. These patterns are really diverse depending on what the user can do. And also it recommends affordances and strategies for music performance. Then, using both systems, there was a large-scale user study that used 74 participants. A first paper deal with embodied interfaces in extended reality. So we apply a mixed methods approach. The quantitative part used the real-time data from the headset. We record this real-time data, and also establish questionnaires like the user engagement scale. And it counts the preferences of the participants in a music performance task. We also use all of these variables in statistics. We apply principal component analysis and also some correlations to figure out what was happening there with these auctions of interfaces. We also apply a qualitative analysis using template analysis. This was done by my colleague, Abigail Fleckenstein, over an open data that comes from the comments from the users and the reasons for the preferences of these interfaces. So we combine all of this to have an integrated assessment of these interfaces, and we have some results here. For group control, there were 3 options of interfaces, and we figured out that these interfaces were system independent. That means that at least with these 2 systems, it doesn't matter which system is. So they work in a similar way in terms of user interaction. So there was an interface regarding or based on the actual reality, some sliders. Another one that was a sort of a panel in which you have to move your hands. And this one portrays some sort of like a magic metaphor, like a magic bubble, in which you can do some stuff there. But what we figured out is that according to the preferences, all the results, these sliders were the more engaging, and the ones the more portray controllability. And even though this one was very interesting and evoked fun or positive emotions, the problem was that there was a sort of lack of precision, and for controlling these complex systems, people prefer to have something that is more clear in terms of functionality. With this one, the problem was the ergonomics. So we have to figure out, or we have the insight that we have to, in a way, take into account the limitations of our body. Yeah. For individual control, we figured out that there were system dependent, actually. So there were 2 options. One option regarding a body dock design. That means that when you have an agent and you open this interface, you can walk around, right? And you can still have access to this interface. The second option was panel dock design. So you have a panel, you put the agent and you do changes. And if you want to move, you have to pull this with you. So this one was more adequate for the Swarmalator system, which promote more spatial exploration and motion. But this one was more suitable for the self-assembly system that promotes more structural changes in the place. Another paper using the data from this large-scale user study was regarding music performance. So there was a task of music performance, and we studied the level of automation, which is basically how can you manage the autonomy of the agents during the performance. So in this case, there were 73 participants. There were 74, but I lost the data from the music performance for one of them, unfortunately. But I have enough. And then we apply also a mixed method approach. The quantitative analysis took into account something that we define as autonomy settings, which is basically the amount over time in a performance in which a participant use autonomous agents and user control agents. So you can see how this in one random participant evolves over time. And then we use some variables from this, especially something that we define as the index of automation, the spread of the agents, and also the time in which you spend in these settings through generalized linear mixed models to figure out how certain properties of the body respond to that, like the distance to the swarm, or the gaze, or the actions that you perform there. And also, a qualitative analysis, which wasn't that much rigorous as the previous paper, but still give us valuable insights, was looking into an audio-recorded interview that was performed at the end of these trials with the participants through a reflexive approach. So from there, we got strategies for music performance. Okay, so as conclusions, we come back to the research questions. Regarding algorithms, we know that bio-inspired models like the swarmalators and self-assembly systems are suitable for music generation and adaptable for user interaction. So the inclusion of individual interactions address the gap of limited individual interactions found in previous human swarm behavior. And in this part, the contributions are the research and development framework, and these 2 algorithms, the interactive swarmalators and the self-assembly. For the second question, system, the transition from virtual to physical, virtual, XR systems, reduce the low embodiment gap. So we can use more our bodies to interact directly with the agents. And the development of this research artifact, the Human Swarm IMS platform, enables rapid prototyping and addresses this lack of standardized platforms for interactive multi-agent musical systems. And the study of these emergent properties and the benchmarks that basically enter in this system-centered evaluation perspective supports insights from the systems with or without human interaction. The contributions are the virtual and extended reality systems that were developed, and this research artifact, the Human Swarm IMS platform. And for the final question, we know the human intervention in swarm system alters their emergent behavior. And these utilized human-centered evaluation strategies address the gap regarding the deeper evaluation of human operators when we study disembodied interfaces and music improvisation, and particularly with these two. For interfaces, we know that the balance between functional and hedonic qualities is paramount, is important. That was also a little bit what I talked about in my trial lecture. And for music improvisation, this flexible level of autonomy allows fluid adaptation for actions, spatial proximity, and visual adaptation. And finally, the contribution from this is a data set collected from user studies and the methods for their analysis. So there is public repositories, public data, totally anonymized, that anyone can use and can replicate these results. So finally, the interaction between a human and a swarm requires a balance of the chaotic behavior of the agents. Although this work haven't found this perfect balance, we don't know. It shows this acclaimed quote in Emergence that says, "The whole is greater than the sum of its parts." Thank you very much.
I now thank Pedro Pablo Lucas Bravo for his contribution. And I call on Professor Stefania Serafin to put the work into an international context, to give her evaluation of the dissertation, and to start the ordinary opposition.
Yeah. Are we switching? Or? Yeah. Yeah, because units.
No, I'm not projecting, I'm just talking. But
Yeah, okay.
Because I see these things here.
Yeah. It's okay. Yeah, let me just put this here.
Good afternoon, everybody. Thank you, Alexander. I think I can put it in my... Okay, so thank you very much again for the excellent presentation, both this morning in your trial lecture and now you gave a very thorough and a clear and pedagogical overview of the main results of your thesis. So first of all, I will put your thesis in an international context and provide you the feedback that you already received from us in a written format. And then there are many interesting topics of discussion that we can take in the next hour or so. So first of all, I would like to congratulate you for the impressive work. You managed in a very short amount of time to cover many important topics in the field of sonic interaction in extended reality. So first of all, you took the challenge of developing a system which works very well and which combines both swarm intelligence and complex interactions in VR. So this requires the skills of a developer, which you became, and we can discuss about development during the presentation. You also became a very good human-computer interaction researcher because you used several methodologies, both quantitative and qualitative in your evaluation. And you addressed both autoethnography and also a very big user study that, as you know, is not often done in our field. So congratulations for that. You also developed several user interfaces, so you have lots of interesting reflections in your thesis about what works, what doesn't. And again, we can discuss this more. So overall, in the field of musical XR, you are definitely a very strong researcher who knows very well the state of the art and went well above it. So your thesis is extremely good quality, so congratulations for that. And again, you achieved in a very short amount of time to produce excellent results. So it was really a pleasure to read. It's well written and it has lots of insights. And also you show that you know very well this complex and very elaborated, diverse state of the art. And also you managed to learn from different disciplines. So it's a very strong interdisciplinary thesis with lots of topics that are very interesting to now talk about. Congratulations for that.
Thank you very much.
So maybe I would like to start just, sometimes when I read a PhD thesis, the candidate starts like with some personal reflection on their background and why they entered this field.
Okay.
And I don't know you personally, and I didn't read that, so I was curious to hear about your history as a person.
My history is a person.
I mean, you don't need to go very personal, just what is relevant for...
I mean, I can't contextualize so until the point that I am now standing. So I'm a computer science engineer. If I'm honest with myself and with everyone, I consider myself more an engineer than a researcher. So I studied computer science engineering in my country, in Ecuador. So, and then, you know, like I think that happened everywhere in the world. Like there are some stages in time in which you have particular approaches for teaching a computer science program. Like at that time was like, okay, let's do web applications, mobile applications, like it is standard boring applications. And then, but something interesting that I would say that is part of like the life-changing thing was that I met a group of amazing people that we grouped together to make video games. So we start trying to make that. We start to study because the program in the university wasn't enough for that. So we start to read by ourselves books and everything. I wasn't that much good in English, so I have to force myself to read like this book in English and stuff. And then like we have a really, was super lucky, a great opportunity from Sony, from PlayStation, that went to our university to have a program with PlayStation 3 for education. But our approach was mostly commercial. Yeah. So we start from that age, like looking at game engines and stuff. We end up with Unity, we have some demo. We show this demo to these people from Sony, and they want to take this beyond. So there was a program of incubation in Latin America for companies, and then they give us the possibility to access to the development kits of PlayStation 4. So basically, I don't know if you have seen, probably you've done, because that's sort of like a secret technology from PlayStation. The PlayStation 4 development kit looks like a toaster, big toaster, like a gray, like nothing like the commercial one. But of course, needs more processing power for like debugging and stuff. And then we start to develop, and we gain more skills and things. That took some years. Of course, like there were issues and stuff. And then like I developed my skills for my collaborative skills, because I was purely computer science, but then I could say, okay, there are more fields. they are the artist. So I cannot like diminish an artist. An artist cannot also diminish a programmer, because everyone was making the effort to build an experience. That was the first thing. A challenge was like the language. What language would we use? Game design. We studied game design. And then like when we finished, I said like, okay, I'm finishing. And something in my bachelor that I was interested in was artificial intelligence and music, because in games I was very interested in music. I sort of empirical musician. I didn't study music formally. And basically I was part of the audio team. So I work with sound designers, musicians, and also the rest of the guys. And then like I was interested in I can like make something a system, artificial intelligence system that play music. I didn't know anything about the field. I didn't know anything about nines or something. And then I started to look at that, and then I discovered this nine community. I discovered the music tech field, and that excites to me a lot. And then I wanted to pursue a master's degree on that, and I could do that like coming here. And all the skills that I have as game developer helped me to follow, finish that master, and eventually coming here, applying that, progressing in looking at the technologies, and basically just I have one day a realization, while I is creating something that is interactive, that reacts at the same time, this boring application. But yeah, that's sort of the story. There are more details and stuff. But
thank you. That was very good.
Yeah, sorry if that was too long.
It was a very nice story. So, embodiment now. Embodiment is one of the big topics in your thesis, right?
Yeah.
And you're saying that you want to use XR to enhance embodiment.
Mm-hmm.
Embodiment is also a term which doesn't have a very precise definition, right? Maybe I would like to hear what is your interpretation of embodiment first.
Yeah, for me, because I remember this topic that I got from virtual embodiment, but immediately if you ask me, it's like the use of the body, the use of your qualities as a person living in this material world to interact with something. So that probably doesn't mean only like touching something, moving something, but reflecting also in how to use maybe the most efficient way, or depending on the things that you want to do, your body for reaching something. And then like you approach something through your body, you have embodiment. You have an embodied approach. Yeah, that's sort of.
Yeah, and why do you need XR?
XR.
Yeah, to reach embodiment.
Yeah, one problem that I found is that, okay, we have these virtual agents and stuff, and we have the robots and things. But the problem with the virtual part is that we don't touch the agents, right? We need to provide more of this like connection of our body, of this like sort of like sensation to reach this. And for physical systems, like one is like, as I said before, for example, you have a drone, you cannot touch it. And the other is like there is a complexity there in building robotic systems. So you have more problems that you don't deal with simulations. So then how can you like provide still an embodied experience? How can you touch these objects, or having some sort of this particular thing into that? So one solution was maybe not the best, XR, because you can have a sensation of the room, you can have the object, and you can, in a sense, touch it, manipulate it, move it, do something even totally different from the actual reality. But of course, I am aware of the problems. So one is like the haptic feedback. So we are just like trying to do something with a ghost, right? Mm. But still, you have some sort of sensation there, and we have this like haptic gloves and stuff that can help with that. But that tried to solve this issue that we have in the virtual systems, and these probably hazards or these complications that we can have in the physical systems.
Mm. But was it important for you to actually see this worm? Could you have a system that you can hear them and feel them without seeing them? Would you consider that an embodied experience?
Yeah, that could be the case, but the problem, maybe there are several problems there. Like if we approach this with virtual systems, or even with the spatial audio, because we have limitations in acoustic, in psychoacoustic. Depending on the application, we might not identify correctly where the sound source came from, and especially in these headsets in binaural rendering. So there is a problem there because that is depends of the person, right? So we have different shapes of here, we have different shapes in the shoulders and stuff. All of these are natural filters for us. And the perception of the location of one source is different from each person. So if you reinforce this with visuals, that would be better. But of course, that doesn't limit the way to make other applications that only you use sounds. So you might not trust entirely in location. You might have a different experience, maybe something in the environment, or maybe something that covers a specific part of the environment, and you know specifically that this is happening in the right. You don't know precisely where particularly, but you know it's in the right. So you can do something there. So it's a matter still of balance, a matter of like looking at the design that you want to achieve. But for me particularly, I was like even excited to explore this in both like audio and visual way, using this embodied approach.
And do you think that there is a specific element that contributed most to the embodiment?
A specific element? Yeah. So the thing is that we might be interested, right, in do some particular interactions. And here, because we are talking about also like if we frame this in extended reality, we can figure out maybe, that depends maybe of the design, new things to use our bodies for some interaction that we cannot experience in the real world, right? So we have physics, right? We have the gravity and everything that in some way can be limited to us. And then if we have these virtual elements, we can explore other possibilities combined with our physicality. We can place, for example, objects in space, like floating around, and then we can have some sort of like dance movement or whatever, interact with the sounds and everything. Something that could be very complicated if you build that in a physical space. So I think it's, in that sense, you can extend beyond the possibilities of the exploration of your own body. And I think that's a contribution that can be there.
Because something that you say also in your thesis is that you use this XR, so this pass-through mode, right? With the head-mounted display. And you say that this mode was chosen to enhance the embodied experience of the users with the system. And are you sure about that?
Yeah, in that sense, the arguments can go through the limitation of technology. Like, for example, I also tried the HoloLens, which is like, it's not pass-through mode. It's like a glass that you have this, this like a square, and you have these virtual things. And then like you can precisely like interact with the objects in the world and stuff, but you have this limitation of field of view, right? And in the pass-through mode, you can provide that without, in a way, this limitation. But if we think about like a virtual environment, a totally closed environment, we might be limited if, especially this case of cyber sickness, can you like promote a more like imprecise way to portray this embodiment into the world? So I could choose doing this in virtual reality, but I prefer to have mixed reality, particularly because I have this device in pass-through mode, for the user to see also the reality and to try to diminish these issues cyber sickness and others, like trying to see also the world. I don't have particular study or from my to see if that actually is the case, but was like my hypothesis. Like I can manage better the interactions in the space when you move in space and everything when you have this pass-through mode. But also I would say one concrete thing that can help with this is that in virtual reality, if you are in a small space, you can collide with a wall, right? So you need a mechanism there are mechanisms to see that you are out of your area, but you immediately don't have that with this pass-through mode or with mixed reality, so you know perfectly that the wall is there, and you shouldn't go beyond that. So it's a matter of like technological constraints and design, and again the experience that you want to deliver. Also, like to try to the user not being like overwhelmed or not suffer for these things like cyber sickness or that sort of thing. Yeah.
So you say that in your very thorough evaluation, the one with 74 participants, you just mentioned that you didn't assess the cyber sickness, but do you have an informal observation? Did anybody get sick and asked you to stop or something like that?
Yeah, that's interesting because of this experience, no one told me that. Even like people that was the first time that they try, and that's something that I try also to control, like with this like service of experiencing extended reality, because many of them were attracted by the novelty of the system. They said, "Oh my God, just for seeing a cube there was so fun." So yeah, that was a thing. But in all the participants, I didn't have any issue. But something that I noticed that I was myself when I was developing this is that I cannot be completely sure of that, but it's an experience I had because I was connecting this with a developing machine, right? So this thing doesn't have the full performance of the internal functioning of the device. This had a streaming. It's a streaming from the computer, and sometimes you have glitches. Yeah. So the thing is that if you are, because it's a camera projecting the outside, right? If you are moving and you have these glitches, it's like you are moving, everything stops. And when everything stops, you feel that you are going to fall. You just fall because it's like the whole reality is stopping in front of you. And I have a hypothesis that I'm not sure, but probably that should be research about that cyber sickness can be worse in mixed reality than in virtual reality in that sense, if you have these glitches.
Yeah, especially with the device like the Quest 3, I think the mixed reality is still very low quality. Yeah. So I don't know, I get much more sick when I see the real world.
Oh yeah. Yeah, that's something that could be evaluated. Probably that depends of maybe the size of the room, the objects, how close you are interacting. Of course, if you want to read something, that will be more difficult because the low resolution. But if you are doing something in a macro way, in a space that is a little bit open, it should be fine. Yeah, or at least what I observed was fine. But of course, I guess that.
Yeah. Also, did you notice were they moving a lot when they were playing with your system, or were they kind of constrained?
So, can you
yeah. So the persons that were trying your systems, were they moving a lot?
That's something interesting. Yeah, they were so concentrated in doing the thing that some of them didn't realize that they could move in space. And if they accidentally were moving back, they discovered, oh, I can move in space. And then they start to pick the thing and going around and like, oh my God, this is so fun. And yeah. So there were some people, and others, like, they never discovered that. They were just like, oh.
Typical.
Yeah. So yeah, that was very interesting to see.
And you can move as much as you, well, not as much as you want.
Depending on the area that you are covering.
Yeah, the physical space.
Yeah, of course. Yeah.
Did anybody have any accident, hitting the walls or something?
No, because was in mixed reality, they could see.
Yeah, of course. Yeah. And then you also talk about the interaction part. So you decided to use hand tracking, right? And why you didn't consider using the controllers, since you mentioned the lack of haptic feedback?
Yeah, that was a trade-off, actually, because I want to deliver this more embodied experience. You have this, right, the haptic feedback that the controllers can give you, but still you have these natural interactions from your hands. So you have to balance that. I said, like, okay, because like maybe how the technology was evolved and everything, we start with these controllers and things, but now that we have this hand tracking that is much better, we can use it to do things. And still there are limitations, of course. We cannot control very precisely as the physical world, but depending on the application, could be precise enough. For this one was like precise enough. There were sometimes glitches and stuff. You have to pick it again, or yeah. But those are things that I think are improving now with also the improvement of technology.
Yes, and you say, let's say that you had the ideal haptic device. How would that look like?
Haptic device,
Yeah.
or providing.
So that you are able to actually feel.
Yeah, I actually wanted to do that, but probably that was too much. And there are gloves that have vibrators, and then you can synchronize with the headset. So in that sense, when you are touching these things, you, in a way, can feel it. It's still not 100% because you have the volume and stuff, but then you can start to have some feeling. And then we have also this vest and this other haptic technology that can help to increase the reality, the sense of reality in that sense.
Yeah, but maybe you don't want to have that, right? I mean, the less hardware, the best, no?
Yeah, and then that's the other thing. Like we are equipping more the body with these things that can have more limitations in the movements and stuff. So it's a trade-off. It's a balance.
Yeah, so you don't want that people that have to try your system, that they have to use like so much time to dress up and be like equipped with a lot of hardware. Also, it's similar to what you were talking about with the audio delivery method, right? Because you say that you are using the loudspeaker in the headset, and they say that they deliver binaural audio because they are they have two loudspeakers. But did you consider, because many times since those loudspeakers are really low quality, let's say, many times people wear additional headphones.
Yeah.
Did you consider that, or?
Yeah, no, actually not. I mean, one thing is like it can be maybe more uncomfortable to wear more stuff on you, and the other thing is that I actually found not that much poor quality, at least from the MetaQuest 3, the binaural implementation that I have. Even it's not like you can see there is like there is a sort of a speaker, like a horizontal speaker, strange design. But my guess is that it's like for trying to provide a more precise sense of space in there. So I found it kind of good enough. But of course, like that depends of the amount of quality that you want to achieve, right? Yeah, that could be explored in the different applications that can be implemented also.
But none of your users commented on the audio quality?
Yeah, actually not.
No, okay.
But probably it could be because the sounds were synthesized, so they expect something that wasn't
That is
like something that you're much familiar with. So they say, okay, this is synthesized, so if this is high quality or low quality, maybe some of them wouldn't even identify that. Yeah, but that's something that could be also evaluated, I guess. Yeah.
And what about because also this morning you had a very nice discussion about reverberation and room acoustics. Is that something that you implemented?
That would be another layer, I would say, that wasn't implemented, but could be also some future work. Probably I didn't put that in my thesis, but I actually have some suggestions from some colleagues and everything when they try this. It would be interesting to also simulate the room acoustic of the place that you are.
Yeah.
But yeah, we need to figure out some things around that. For example, the computational performance. The hexes have to analyze what is actually around, which It does, in a way, for establishing the boundaries. But yeah, it might require more like computational power and more development time for reaching that. And for some experiences, maybe it's not that needed. And something that probably I didn't mention in the trial lecture is a way to optimize things. Because, for example, in games, when you have an open world, you don't have rendering of everything, right? Depending on how you progress, the things are rendering as they come. So these optimization techniques or other kind of techniques can be also used for room acoustics if we need room acoustics. Yeah.
Yes, and another aspect that you touched also this morning, and also you have in the discussion of future work, is about that this mixed reality or virtual reality experiences, they're usually kind of lonely. So there is a person interacting with a virtual environment, let's say. And you discussed that it would be very nice to have a multi-user, so collaborating in interacting with these swarms. And maybe you did already a little bit this morning and also during the presentation, but can you maybe elaborate on how hard it would be for you to create a multi-user swarm?
Yeah, thanks for asking. That's actually a next project that I'm thinking in doing. Actually.
Oh, awesome. Yeah, nice.
Yeah, there are some difficulties there, but I will figure out. The other thing is that when you have multiple users, of course, you have to synchronize the space in a way, right? And for that, you can think about like the multiplayer games. So in a multiplayer game, you have several challenges to solve. One key challenge is the networking. So if we think about the technology, so these headsets have to be synchronized. They have to be connected between each other. And that's one thing. But the other thing is the synchronization of the space, the shared objects. So I haven't gone like yet into that with these particular technologies, but that's the next step I want to take. It's like, how can you share the object? Like, for example, in one of the examples I showed in the trial lecture, there was this like badminton game. Yeah. So basically, there were 3 people sharing the same object, which was the ball. So in a way, each one have to have the same perception in a space with this object. So there are some techniques I still have to figure out how that works, in which you have several anchors in a space that can synchronize the space so that you can have access to the same objects. And this idea, like I like it particularly because once I remember there were the childs from some colleagues coming to Remo and they tried the headset with these systems. And I have 2 headsets and they were like doing their thing. But the little girl wanted to give me a cube or want to share the cube to the other. But of course, it wasn't possible because the space are not synchronized. So then like, okay, maybe it's a good thing, like deliver this experience of shared objects. So yeah, it's something interesting that we'll explore more.
Nice. Yes, you have. There is so much to discuss about. Another topic that is really important is the mapping topic. So you showed us some very nice. You showed us basically the final product and the 2 approaches, like the individual and the collective control. But maybe can you elaborate on your process? How you, because there is the mapping. So there are lots of mappings actually involved in your multisensory experience. So there is the mapping between the gesture and the objects, the swarms. Then there is also how you map the sound to the visual. So maybe let's start with talking about your thought process. And I assume you had some sort of iterative development before reaching the not final, but the current implementation. Yeah. So if you can discuss a little bit that.
Yes. Yeah, that is something that can take several directions, right? Exactly. Because we are talking about a swarm system can be defined as a complex system. So we have several dynamics that we can use for sonification. We can have like several parameters, several ways that even cannot be identified at first, because this is something that we have emergent properties from the several interactions from these agents. So this is basically like trying to see, okay, first we have this swarm system, this algorithm, and these are the dynamics. So I put the example of one of the system, the swarmulator system. So we have a model, we know how it works, and we figure out what are the parameters that can be controlled globally. So those parameters that can control globally can be used in an interface, right, for changing them in real time. So in the case of this formulator system, there is a mathematical model. There are two parameters, J and K. And if you tweak that, you see all these emergent patterns that I show in the presentation. And you can do that as a user. So that is a way for group control. Seeing the dynamics of the algorithm and then like looking at the parameters that you can modify for the group control, and provide a way, which is like an interface for modifying these parameters if we want to introduce interaction. Another example I can put is like the example of the voids, the birds, right? A really simple approach is that a bird like when flying these patterns, the bird want to go together with another one, but also don't want to collide. So you can have two different radius there. So you can approach this as a global parameter. Like for example, all the birds has the same value for one radius and for the other one, for no collision and for following. And you can have an interface in which you change those two. And when you change it, you see how emergently the patterns changes in group. So that's another example of how to approach group control. And then we have individual control. So in individual control, we look specifically on what can we change for a specific user, for a specific agent. And in the sense of this system, the swarmulator, again, you can look for the changes of these particular global parameters, but in an individual way. So that is one possibility. And you can provide either way, like something through an interface, if this is too abstract, like for example, in these dynamics, if we want to map this with musical notes of frequencies, the interface can change individually these frequencies. But if this is something very natural, as like moving something in space, I can, with an interface, change X, Y, and Z. But if I have a system like XR, I will not do that. So I just deliver the way in which you take it and you move it. So you can deliver this in both, in an embodied way or through an interface. So that's individual, in the sense of individual interaction. It corresponds to the dynamics and interaction, but still we have the part of the sound mapping. And then you have a lot of possibilities there. And that's also that I said also in the thesis that this thesis is mostly about these two parts, the swarm dynamics, the user interactivity, and the mapping is not that much explored. That's future work. But still there is an initial approach to try to see some properties that might serve for some sonic interactions or particularly for music interactions. Like, for example, in the case of the swarmulator, there is this phase and position parameter of this internal oscillator, this phase. So this phase is mapped to the pitch of a sound. So when you have these different patterns, these different ways to synchronize and unsynchronize, so this pitch parameter is changing. So that's a simple mapping regarding that. We can limit this mapping into something more discrete for achieving musical notes, for example, not necessarily something continuum. And then we have some sort of more musical thing. But of course, apart from the individual mappings, we can use global parameters for global mappings. Like, for example, let's say that we can calculate for all agents the center of the swarm. Then we can map the movement of this center with something else. that can be like distributing in each agent, or maybe there is another sound source that use this central parameter for mapping. So there are many possibilities in terms of like individual dynamics and group dynamics that you can map. And I guess that is mostly something about exploration, because you can have something very annoying with a certain system, or maybe something very interesting. And if I have to classify my two systems in the annoying one and the pleasant one, the first one, the formulator, is the annoying one, and the other one is the more pleasant one, the self-assembly. Yeah.
Is that your classification, or
It's my assessment.
did you get the same feedback from the?
No, I just thought of that right now.
And what about because you have all these objects that have colors, of course, and there are lots of theories on how to associate the sounds to color. Did you follow them, or what was your process through choosing the colors of the? It's fine if you didn't, because you have so much to.
I was thinking, because like probably I look at that, but I didn't put much importance. Because what I wanted to achieve is like a clear identification of visual feedback with the sound. I don't know if there is a particular scale. I could say like probably like the range scale of in physics, where you have about the colors. That could be something that can map to that. I don't know if that can be mapped naturally with user interaction. But yeah, I mean, there are also several design decisions that I could have taken around that, but probably that wasn't thought that carefully, because there were several focus.
Yeah,
right?
exactly.
And I couldn't cover everything. Probably there are a lot of design issues there still, but the main things I wanted to cover are there. Yeah.
And another thing that you're talking about is where the objects are in space. And this morning you said something interesting about bending spatial rules, so that you can have a sound that is in one position and then an image, like the visual representation somewhere else. But in that case, the user is not going to consider that as a unique audiovisual object, right?
Yeah.
So what are you bending there?
Yeah, that's as I said, like that depends on the experience. So if you want to deliver a more like congruent experience with the physical world in the space, so you can, of course, you must be congruent with the objects in space. But this particular case points towards more like I don't know if I can name that correctly, like that, like crazy experiences. If you have like in a game, in the game the main character is dreaming something, you have a very precise game in terms of like the reality and everything, but then you want to provide a dream. So you might use these techniques for having something that doesn't correspond to the reality because it's intentional, right? I intentionally want you to be confused and seeing something there, but listening something in the other side. So again, that depends on the design, but it's a possibility, like blending these spatial rules for providing something out of reality.
Also with the dimension of the space, you were thinking, like?
Yeah. I would say that probably there are these tricky, how is it called, these forms that has like a strange connection. I don't remember, but you can bend the space also to give these tricky experiences. So there are several possibilities that you can do, and especially considering like virtual reality and extended reality, and even like I think I have seen also that in mixed reality you can have a scanning of the space in a way, and then trying to deform the actual reality. So you have this blending that is sort of again crazy. Yeah.
But when your 74 users, they tried your system, probably more. That was part of the evaluation. What I didn't read much about how much training you gave them. What did you give them some specific task, or what was the procedure there?
Yeah, so the procedure was like there were two two objectives, right? So one was like evaluating the interfaces, and the other one is seeing how they make music in a way. And of course, like when I recruit like people that wasn't necessarily musicians, because for me it was interesting to see, okay, if you are not a musician, what can you do also in this system that the musicians don't want to do, or like feel limited. So yeah. So one thing about the approach of the interfaces was like in the trial, the user came. I explained what is this system about, and then like the participant filled some questionnaires regarding the experience in XR, also musical experience, and then like methodically there were like all of these interfaces options delivered to the participant. And the first intentionally was this slider, because it's one of the arguments that is the most familiar interface that you can have in reality. So with that, you can explore the system. You can see, oh, what is this? So then you change, you see what is happening. And once you are familiar with that, you can focus a little bit more in the other two. Yeah. So there is a limitation there, because of course this is controlling the novelty of the system, but still I decided to include that because I was interested to see, okay, like people still prefer, even though they after that they try these two other interfaces, they still prefer this one. But the other interfaces, I switch the order, I randomize. And they try that, and then in the middle, before the individual interactions, because I didn't activate the way to manipulate the agent, so they were like just like they couldn't grab it, because I want them to be concentrated in the group behavior. In the middle of that, I put something to control the novelty of picking the agent. So then they have some exploration of what can I do with them. I can pick it, I can throw it, I can do this. And then after that, there were two subsequent interfaces for individual control, in which you can use both the individual interactions and then some changing in the specific parameters, right? And then afterwards, they have to choose the preferred interfaces for a music performance. So from the group control, they say, okay, I prefer the slider, or I prefer the magic bubble, or whatever. And then for the individual control, they have to choose one of them, and then they have free time for doing what they consider to be a music performance. Yeah. And basically, with these two approaches, and after that we have an interview and another final like a form. With these two approaches, I wanted to see the part of the interfaces and the part of the task of the music performance. So that was the thing how it was evaluated, like this approach in terms of interfaces. Yeah.
And did you mentioned also this morning that importance of presence, especially when you consider virtual environments. Was it important in your, so the sense of presence, that the user feels present in a virtual environment? Mm-hmm. Is that something that you think it is important in a musical context?
In this, it's important. I mean, because like you have this, you are telling beforehand to the user that you will be in this environment. So it's some sort of expectation. And whatever experience you want to deliver to them, so they have to feel that they are into the environment, in presence there. So if there is some sort of disconnection with this expectation, I think that can be problematic for the task at hand. Probably I have to look more in depth into that for sustaining that argument, but that's my feeling, that you cannot disconnect for the experience that you have to deliver, and the presence have to be there, because this is something else that you are trying to do, and there is this expectation also.
Did you, can you elaborate maybe a little bit about, so in your usability or in your user experience evaluation, that was extremely thorough. And you have also a lot of research questions, especially in paper 7. You have like many questions and sub-questions. And maybe the most interesting part is the aesthetic quality, because it's a musical experience, right?
Yeah.
And can you elaborate on what the participants said about that?
The
Is that,
aesthetic
is that
quality.
something they would use to make music? Because it's like a musical instrument, right? And you don't learn it in in the time you have to,
Yeah, of course, I'm not a visual designer. So the designs are mostly from
Sorry, I meant like aesthetic quality of the overall, also the sound, like the whole
I mean, like
package.
I thought with my intuition in how to model that, and but I received critics about that because there were some like visual designers there. They said like, "Oh, look, you can use this different color because of this and this and this and yeah." But of course, like if someone knows about that, are going to point out that. But the worrying part is like for people that don't know, it's impacting them indirectly, right? So part of the design is also the visuals. If we're going to deliver a visual experience, also we have to take care of the visuals. So that's why usually, or ideally, this kind of systems and that happen in games, right? There are people that is specialized in the design, the visual design. But I got, probably I didn't put directly in the results, I have it in the data, but I have some people that was telling me very useful things regarding the visual design that I have probably to check for.
And what about the sonic design?
Yeah,
the quality of the
sonic
sound.
design, in that sense, is something that I also point out in a way. The focus wasn't much into the mappings, and of course I have some people that were more experienced in sound synthesis and sonic interaction, and they would like to have more diverse mapping, maybe more complex things. And particularly in the interfaces, I didn't deliver controls for sound properties. It's mostly about the swarm dynamics, and this could be also future research, is like delivering the control for specifically the sound properties that you are hearing, like modifying the mappings that are there. So yeah, I got comments about like that maybe I can use different approaches for the mapping, but of course, as I said previously, that demands a careful design because you can have something super messy with a swarm system. Yeah.
And you try to put all these design principles, especially in your CMMR paper from 2023. That's like you are proposing a framework, right? When you're looking at all these different elements. And maybe we can look at some of the most interesting one. It's like we didn't talk much about, probably we'll talk about in the next part, about the human-swarm collaboration. And how do you say that it is, I mean, when can you say that you perceive the swarm as collaborators? Like, when do they have agency? How can you determine that?
Yeah, that's something that is complicated in these systems, actually. Yeah, is that the catchy part of my title? But it's it's a trade-off there, of course. Because these systems are complex, they might not be that controllable, and that was the point, trying to find a trade-off in this sort of controllability. So it might be difficult to see how you can collaborate with them. That depends of the algorithm, that depends of like the ways to interact. And that's why, for example, in the field of human-swarm interaction, human-swarm in robotics, human-swarm interaction, they look at actually reduce the complexity of controlling a swarm system. They don't want to look at the individuals there. They want to look at as a whole. So in a way, you can team up with the swarm to solve a specific task, and you can say we are collaborating because they are looking at things. In this risky operation and saying, okay, you have to go there, you have to rescue that person, and so on. That's a way to collaborate groupally. But for music systems, we have a very wide approach in a way. And that's why also like the individual interactions are important. So the collaborations can range very differently. And that's also what I observe in the participants. And I think that one interesting thing is like some of them were very amazed for what they were doing. They were just observing and seeing, okay, I can do something else, but it's very nice. But some others want more control. Yeah. So there was a clash there. So, okay, they are doing this thing, but I can do something else. Or maybe there were others that in which, okay, they are doing this, I can follow them. So yeah, there are several nuances. And I would say still that is some sort of like collaboration in a way. But this has their trade-off. And that is very dependent of the intention of the person.
Yeah, also something that is interesting that you mentioned is that these techniques are used mostly in robotics. But in robotics, of course, we have different demands. And maybe failure is not accepted as much as in musical interaction. Mm-hmm. So maybe if you could discuss which kind of failure you encounter in your very complex system. Mm-hmm. And what is a failure and what is a feature in a musical experience? I can give you an example. I was at one of these computer music conferences some time ago, and the performer was playing something, and then she stopped and she said, "Oh, sorry, there is a mistake," and nobody had noticed that. And then she went back and she started again, and then she said, "Oh, this time it works well," and nobody could. So.
That's very typical.
Yeah, you shouldn't stop right when you perform.
Yeah, I mean, of course, when you're, I don't want to like throw this critique, but I will do it. And in NIME, usually you have these interfaces and performances that you can't identify if that is part of the performance
or if it is a failure.
I actually personally call it the fancy noises. So yeah, the thing is that, of course, if you have a physical system, you can face different sort of failures. Like, especially if you have a centralized system, I mean, if the central point fails, everything fails. That's why ideally you must have the centralized system. So, and that's actually the good thing about a swarm system. If one or two fails, the other ones can still do the job. But in this system, these XR systems, we can consider, like, even though like some inner workings can be considered decentralized, technologically it's a centralized system. So failures we can encounter and have encountered can be like glitches from the technology. If you don't balance properly the computational power, you can have frame drops, and you can stop, like the interactions can be like no much fluid. But sometimes you have, like, because there is these glitches, and they can transmit to glitches in the thread in the sound. So then you have something continuous and something happen, and depending on what you're doing, you can say, oh, that was part of the performance. So it's possible. It's possible also to have these kind of things. But one interesting thing that I can take about that is that when you experience this, you can say, as you mentioned, that, oh, this looks nice, it sounds nice. I can have this as part of the features of the system. And you can intentionally include and try to model that as part of the system. It's the famous phrase of what's this painter, Bob Ross, I think. It's like a happy accident. Mm-hmm. So yeah, you can use it as a feature. But yeah, something that again that worries me because of this experience that I have with when I was developing this totally like stopping of reality where you were working. That's something that shouldn't happen. Never happen. Yeah. You shouldn't like stop this. This like action perception loop is basically it's disruptive. So it's even if you are in crazy world and whatever, you have to work into the congruency of this world. That is totally out of place. So you disrupt that, you can even get hurt, you can fall. So we need to avoid that, but also look at these happy accidents.
Yeah, because maybe also what you were talking about before with the hand tracking, that sometimes it doesn't work. But then if it works like the second time, that maybe the person doesn't consider really like a bad failure, let's say. But if it keeps not working, then that might create some frustration. So it depends also.
Yeah, there can be, because at the end they are still aware that this is an augmented technology that might fail. If they see that something fails, maybe they will not disrupt that much, and maybe they will walk around the thing. But of course, it's a balance. There is a balance there. So we need to provide the less failures as possible that don't disrupt the presence in a way. Yeah.
And maybe since you also mentioned, again in your CMMR paper, you mentioned accessibility and inclusivity, but you don't elaborate much on that. What did you want to talk? What did you want to say there?
Yeah, accessibility also something that I didn't take care that much here, because depending on the physical capabilities of someone, the experience might not be fitable. And also for that paper, we have a very limited amount of pages, so I might say a lot, but I was limited. But yeah, if we want to approach the design for accessibility, that depends of the type of experience or how the people with maybe some disability can still enjoy these sort of experiences, right? Maybe hand tracking is not feasible for some of them, so we have to approach the design in a way that we can also fit into deliver a similar experience, and still the experience is enjoyed.
And maybe one last question, because I see time is running. You say that you derive from robotics. What can you teach? So now you're focused on musical improvisation. What can you teach to other fields like robotics or game design? So what can other disciplines learn from your thesis? And also you mentioned in the thesis that you're making a contribution also to the field of AI. Maybe if you can elaborate on how your thesis can be contributing to other fields.
Yeah. So for example, in the case of robotics, of course, there is particularly one concrete, which is this self-assembly algorithm. So it's something that you might approach physically, but of course, you have to solve all these issues that are behind that. And also, there is a particular concept in human-swarm interaction that is called neglect benevolence, which is basically when you have this swarm system, you have to wait for the swarm to converge to something to approach other action. It's like a natural delay of the system. That is not a technological thing; it's part of the design. So part of the research is also mentioning about that, about the people that also could identify this. They say I couldn't do this because I have to wait for this to happen. So these are insights that can also contribute in a way to this human-swarm interaction field from robotics. In terms of game development, that depends if you want to do experience that includes swarm systems. There are some insights about the interfaces that might be included in game design. Also, particularly in terms of technology, there is this paper for the sound engines. Basically, that serves for many other fields that would like to include sound synthesis into the headset built-in. Yeah,
That's the C sound versus
C-sound and
Chuck.
Chuck.
Yeah.
I sent the paper to Yiwon. Yeah, so he said, okay, I will read it. We will solve that issue. Okay, I hope that they will solve it. Yeah.
Well, I think I'm going to stop here.
Okay,
thank
you
you
very
very much.
much. Nice.
Congratulations. Great job.
All right. I want to thank you then, Professor Stefania Serafin, for your contributions. And now we will take a little break. And after the break, Associate Professor Kevanch Tatar will close the ordinary opposition. But first we'll take a little break, and we'll be all back here and seated by 5 minutes past 3 when we will start the next part of the session. Okay. Distinguished members of the committee, dear colleagues, ladies and gentlemen, welcome back to this public PhD defense of Pedro Pablo Lucas Bravo. We are now in the last part of these proceedings, where Associate Professor Kevansh Tatar will close the ordinary opposition.
Just testing. Great.
Yeah.
Thank you for inviting me, first of all. This was fantastic. I mean, I'm so happy to read this thesis. It was so thorough, and also I was also the external examiner of your master thesis, so it was really, really nice to see how much you have done since then. In a very short time as well, in just 3 years, this much of, the amount of research coming out in that short time is already quite impressive. I can quite well see the depth that you went in your research efforts, which is great. We are really, it's unique to see this level of depth and enthusiasm as well that's coming out in the text and the dedication. So these are all great things, and so there's no question in that sense. What I'm going to ask in the next 30 minutes to an hour is more, I just want to clarify that I'm asking these questions because I'm really interested in your work and I would love to learn more about it, rather than more of a, I'm not necessarily interrogating or anything, more just trying to understand different aspects of it and trying to dive in a little bit deeper of some of the topics Stefania already covered, but also, maybe some other aspects that are more machine learning and AI specific. So I want to start from putting it into maybe a right context from the music and sound synthesis. So that's one thing that I was a bit, not to say confused, but it wasn't so clear to me that if some of them are systems of sound synthesis, or are they systems of music, or are they an material of music in and of itself as maybe a generative music, composition, or we could have all these different terminologies in that sense. So where do you fit all these work?
Yeah, that's a good question. Because something that I don't look deeply, because there are many things to approach, was the context of sound generation. I would say like I taken this for granted in a way. It's part of the thing, and actually I realized, like building the trial lecture, like there are many components that can't even fit in the things that I'm doing. But I would say that it's also in a way has to do with this simplistic, or like this approach that I gave to mappings in favor of swarm dynamics and user interaction. So in that sense, in terms of sound generation, what I can say is like, of course, I'm using sound synthesis there. I'm not using sample-based approach, because this is also, I mentioned in the trial lecture, I want to provide continuous interaction. So the most fitable thing for this was like using synthesis. But in terms of synthesis, in the mappings, it's described that is something usually very, very simple, like for example, sine waves. And those sine waves are modified. There are some modifications in terms of envelope and of course frequency. But the thing is that the modifications that actually came out emergently with the sounds are performed through the swarm dynamics. So I could argue that this is sort of, again, like sound generation, sound synthesis, contextualized in that sense through a swarm algorithm. Even like you can argue that this is a sort of granular synthesis, but the composition is through a swarm algorithm. Yeah, maybe it would not be that precise, but it's something that you might frame with that.
So do you position it more as a sound synthesizer rather than a music system?
Yeah, then I would like to know also like the your vision, what means for you sound synthesizer and a music system.
Good question.
Yeah.
But I'm not defending here. So that's the question here. What is for you the difference between a sound synthesizer and the music? So also that in foundation, that has the question of what is music for you? Because that could be a different definition for different contexts, right? So
Yeah,
what I'm trying to do here more about just tapping into your understanding of music, how you conceptualize it, and how that reflect into this defense. But also through that, I'm trying to understand these systems in the way that, so where do we categorize them? Where do we position them in the landscape of, we have sound synthesizers, we have instruments, musical instruments, and then we have these generative systems, and we have machine learning and AI systems. So if I look at these systems, and you can give examples because there are a few and they can be different, I understand. So if you think about that landscape, how do you position these technological objects, methods, approaches in that landscape?
Yeah. So I would say directly that it's a music system, because like a synthesizer is the tool that I'm using inside the music system. That's why for me it was a little bit confused. Like, okay, synthesizer you can see as a music, because with a synthesizer it's like like a tool that you can use, or like a procedure or something. You have all of these parameters, you can do all these manipulations, but something that also again can be arguable is that you don't necessarily want to make music. But also the concept of making music, that depends of the person, of course. But I see it as a tool.
Yeah, I see. But it's used in making music, right? So then my follow-up question is, if you want to contextualize these in a music-making scenario, and also it touches a little bit upon one of the Stefanios questions about the aesthetic qualities, the sound aesthetics of this. So how does it connect? How does these systems fit into a musical scenario, what those musical scenarios are? Like, try to give us an imagination of what kind of musical scenario this is, what kind of musical context this is, and what kind of sound aesthetics are we talking about?
Yeah, I would say directly experimental music.
Experimental.
But that would depend also of the implementation of the system. But I will push that mostly into that because of this complexity of also controlling the system. So you can be more experimental, and that was actually the approach of even the musicians that try the system. Because like some of the musicians say, okay, I know this thing, I'm a musician, I know how to do this. And they try to, for example, form chords or some musical structures. But then they look at the dynamics is like pissing me off. So then they say, okay, I quit, and then I will do more something interactive. But still I want to try to have a context of music within that. So I would say it's more experimental, towards experimental music.
And you mentioned complexity. So what is complexity in this context?
Yeah, complexity, it could cover many areas in this work, because we can start with complexity in the swarm system, in the dynamics, in the inner workings of the algorithm. Because we have all of these small interactions, and we don't know what is happening until we have some sort of simulation or a way to run this and see what is emerging from this complexity. And then it also like give us a complexity in the interaction. So depending of what you want to do, you want to reduce that complexity. So in human-swarm interaction, you actually want to reduce this for controlling this as a whole, right? But in the case of the music systems, you might need to have some flexibility or embrace a bit the complexities of the several parameters that you can modify for the interaction. And then maybe the complexity can be shown or reduced in some parts depending of the experience, the interactive experience that you want to deliver.
But tell me more about the complexity in the swarm system. So why is it interesting musically, do you think?
Yeah, it's interesting because it's like there are several variations that you can have that could quickly can arrive to something very, very, very messy. But if you try to control and you figure out what can emerge from that, you can have more concrete mappings for something. It could be environmental sounds or whatever that can fit into your design. For example, the case of these thermalator systems, how it's mapped now, it can be a bit messy. But if you carefully know that you have these macro patterns, it's something that is studied, the macro patterns that I showed before. So then you can say, okay, I can carefully have mappings knowing that I know these emergent properties for something more congruent, something more pleasant, not much random, because I know these emergent properties, right? So in that sense, you have this sort of complexity in this one.
Interesting. So there you are sort of describing a familiarity with the algorithmic approach in your case. And you have the familiarity with the swarm system, so you can plan with it in some ways. But I would also assume that not many people has that. And I can see that, like, in your work, you have autoethnographic work, which is great. We want to see that because we are also interested in your familiarity with these systems because you spend so much time in them. But you also did user interaction with like these very wide, 70 people user interaction studies. So do you see a difference there? Like, could you tell that like, oh, they were lacking familiarity, or could they grasp familiarity immediately with that complex system?
Yeah, that's actually a question that I asked that is not part of the research because like that's, I would say, future work. I asked them to describe the behavior of the swarm system. So in the few answers that I saw, like some of them have a very rough idea of what was happening. Others like describe something totally different. But in a way, I can say that they, into their inner thoughts or whatever it's called, they figure out that they could see something, maybe some patterns that can help you to continue in seeing how can we interact, what is the next interaction that I should do to reach something. But of course that implies at the first some sort of like exploration for the system, right? And then like you could figure out that, okay, in autoethnographies that I did, I figured out all of this because I know the system and things. And the others, they didn't discover that. But there were some components from this that the participants discovered were more logically there and they could realize. For example, in this self-assembly system, one technique that also is in one paper, in the paper, and also like I could figure out with several participants, is that when you have structures, small structures, they have a lower tail in the envelope, so you can have something more melodic. But if you have a bigger structure, the envelope is, the tail is longer, so the things overlap and you have something more harmonic. So that was something that also some people discovered. Some people want to have their own like clusters of agents to have some sort of, I would say, identity, musical identity, if I can name it like that, for their compositions. So this is. I mean, I can say that I discovered things that I didn't discover. That was also the point for having all the people. But they also didn't discover other things, for several reasons. But yeah, it's something that I can compare between those two.
And what you described there is sort of connecting the behaviors of a complex system or an AI system to musical meaning or musical affordances. How do you think we could study this if we want to study this in future?
Yeah. The complexity with affordances, I would say that is a task of human-computer interaction, right? And then you need an artifact, the system, and study these properties into the artifact, into the system. So then you might evaluate specifics about some aspect of the design that you are putting there. And then you can have design insights that can like fit future designs and the affordances. What can I do with this? What can others do with this? And if the others already know, so what are the next steps? How can I improve this to have this interesting affordance that I didn't know that exists. So it's something that you can explore with that, with several iterations. Yeah, it's a matter of like maybe also a study from a quantitative perspective and a qualitative perspective. Especially the qualitative one is the one that tells you the whys. Otherwise, you have a bunch of numbers with no meaning. So yeah.
Great. Staying on the swarm algorithms, I have some questions. It was refreshing to see something that doesn't just tap on the trends going on. But at the same time, the question is, and this is always the question for any algorithmic choice, why swarm algorithms? Why not any other artificial intelligence approach or machine learning approach?
Yeah. The swarm approach or swarm relator? If I understood correctly.
My question is
swarm,
like
the swarm.
Swarm.
A swarm system.
Swarm systems, or it's a artificial life sort of approach. So, and then you are focusing on the swarm.
Swarm system
approach. I mean, you are focusing on a few alternatives, but at the end, we can just maybe group them into as you said, swarm intelligence sort of approach. But you could also use all sorts of different other fields. I'm more on a broader superficial state here in the discussion. So why not other fields, but focusing on the swarm approaches, swarm algorithms? What is unique about them? Why are they interesting for music systems?
Yeah, of course, we have different approaches for interaction, also music generation. But what I found interesting in swarm systems is that this emergence. So things that you might not know what is there, you have to put the thing, run it, and see what is happening. And for me, that might trigger creativity in a way for a person that can interact with that, and in a way can like emerge some creativity depending on the right mappings that you can portray there. And I think that the approach of this emergence that comes from these algorithms is something that is appealing. Well, also that was interesting for me to see what can you get out of something that you beforehand don't know how will behave.
Very interesting. And how to study that also, right? Because you need to understand the participants' engagement with it. And also in music and sound, we have special contexts, I would say. It's a very particular domain. We have our own lineage of sound studies and such. So, but when I look at your thesis, most of the research is coming from the human-computer interaction, which I wouldn't necessarily say that the sound studies knowledge is often in there. So if you would, for example, let's say with the knowledge that you have, if you would go back to some of these studies, but you also want to really focus on the sound aspects and the music specific aspects, how would you change it? How would you update your approaches?
Yeah, so there is something that actually is part of the future work because, of course, as you said, like this is heavily, especially in the last two papers, human-computer interaction. But for looking at the sound and the music output is going directly to that, and that's something that I have but I didn't analyze, is the sound output, right? The things that you are getting from these performances. So we have all this signal that we can analyze from different approaches. We can even have like a qualitative, like hearing that and seeing what patterns we can take out of that. Also quantitative, like with music information retrieval, seeing how these approaches can merge to see the product itself. It have some particular, let's say, meaning for the process itself for doing this, for the interaction, or also for the person, or even for audiences. If we put this with a group of people, what they would think, do they will like this music, or like how they will react? So I think an important part here is the product, the sound, if we want to study in that sense.
Which is Gestalt. You also briefly touched upon the process. You said we also should look into how we make it in the first place. So can you unpack that a little bit? Like how would you look into that if you are, would you like to look into, musicians trying this? Would you like to look into, everybody trying this. So what would be that?
Yeah. So now the approach that is here is trying with everybody, basically. And I argue that it's like something that can be useful because even the musicians probably are limited to their knowledge. So we don't know what other affordances in the first place we can have. And we can discover that maybe with users that maybe are not musicians. But then once having this, of course, another step can be training musicians, like electronic musicians even. And there could be a lot of insights about how the interactions, particularly in sound, can be implemented here. Because here we have mostly the dynamics working in there. But still, for leveraging the system, we can include interactions with the sound properties, the volume, the pitch, other properties from the sound that can emerge from the dynamics. We can have, I would say that we can have like another layer of complexity to this, the complexity of the sound into the interaction for making music.
And in terms of the swarm approaches, so that's one of the artificial live approaches, and there are quite a few others. Like, is there any other approaches, algorithmic approaches that you would like to also, investigate in that setup?
Yeah, I mean, more than a live approach, I think about in the field of multi-agent systems.
Yeah.
Because something that I also mentioned is that there is this traditional classification, right, of the reactive agents and these cognitive, like interactive agents, as they are so called. So the thing is that we can have a higher intelligence, not only a simple intelligence. So then we can see how the elements or the agents that have a higher intelligence can interact with each other and with the user in that sense. So most that maybe exploring other life approaches, I would like to look at this concept of game theory, for example, in which you have like negotiations, auctions, these kind of processes that are closer to human interaction, right? And then we can see how these systems, more than react, also interact with this more complex, let's say, way to communicate with each other.
I love that we are moving into multi-agent systems, my favorite topic. So some questions there. You mentioned multi-agent systems, but when we define an agent, we often think about, there's an agent as a perception capabilities, it can act in an environment and such. So in your systems, how does those individual agents perceive? What do they perceive? That was not so clear to me. Can you a bit clarify?
Yeah, because this is like basically a centralized system. I mean, of course, ideally, we need decentralization in a swarm system. But in terms of technology, they actually know each other. So the way to communicate is like part of the inner workings of the algorithm. In the case of the first algorithm, the swarmulator, so listening means to know the position and the phase of the other oscillators in the environment. So now it's centralized. That means that every agent is aware of all the other agents, no matter where they are. But if we want to implement this in a real setting, so we can use a networking system, or if we rely on local cameras, or even in the sound that they are generating, we need to have more sensors, right? And that will be decentralized, and the communication will be different. So in this case, I would say like the communication is the inner workings of the algorithms. This first algorithm, swarmulator, is aware of this. It's like a message base, I would say, but it's directly injected into the inner workings of one agent. What are the positions at the face of the other ones? And in the case of the self-assembly, that's a little bit more decentralized, I would say, because they are not actually looking at others. They have a radius. And when they detect another one, they say, okay, I will join. but there are a set of rules for joining or not. So that's more decentralized. And that could be like if we have sort of ideal robotic system that could be kind of immediately implemented into a physical system. But of course, there are other issues to solve. But that is, I would say, that is not a centralized approach. And the communication is, I have a detection radius, and with this approach, something is happening. I detecting that it's there.
So give us a bit more information about how you design a system like that. So what you are describing is you are sort of designing complexity and emergence by writing a set of rules, right? And in this context, you are making those rules specific to sound generation in some ways, because that could be through mapping or it could be embedded in the design itself. But give us more information about what is your process in designing a system like this?
Yeah, okay. So in the process, we need to choose, of course, a strong algorithm if we decide to go for that. There is an architecture that also is there, the PQF architecture, that is a synthesis, process, analysis, process, and synthesis with a knowledge that you can use for the swarm. So you have the swarm there, but you need to input the swarm in a way if you want to interact with that. So you have to deliver the right properties that you want to control, and then you have to say, okay, how the information that is giving me this algorithm will be out of the world through this synthesis part. So yeah, one thing is like the algorithm, and now that we know the inner workings of the algorithm, so we need to know in terms of interaction what we need if we are putting a user there, and then how we synthesize that. Again, and in terms of these systems, they are framed in this architecture, and if we frame this as fully only autonomous, of course, like in terms of user interaction, they will not have the input from the user, so they have only the inner workings and whatever is happening in the environment. But still, they have to synthesize that. And they have some knowledge inside to solve these inner workings. So I would say that you depart from this, and then you have this bigger perspective of how you put this in an environment. And then depending if you want to deliver user interaction or not, you have to work in how you inject this input. That in this work is through these interfaces and the way you interact in a groupal and individual way.
And when you talk about that, for example, it's designed in a way that the user controls the whole system. And I want to touch upon this control aspect, especially in connection to agency. I mean, so we have here a control system dichotomy in some ways, which is also similar to control and synthesis dichotomy. We also have a lot in digital musical instruments. Is there another way of doing this where you wouldn't have them separated, maybe?
You mean separated the control paradigm?
Yes.
With the
system itself.
Another way for interacting without the control paradigm.
Sorry?
Is that the question?
My question is so you are taking the control out of the system, right?
Yeah.
Where you have almost a sort of like a direct engagement with the general properties of system. The user can immediately, change what the objects are doing. So there's almost like a total control over the individual components of the system. Yeah. And for that, you also have, for all those control, the agency that you give to the user is a full control over the system through these, sliders and whatnot, or, throwing things in there. That is one way of doing it. So in that case, user have a control over the full system. But do we really need that separation? Is there any other way where we wouldn't maybe have a control system separation, but it would be a different approach where that is maybe more decentralized or distributed? Well, how would that look?
Yeah, okay. Okay, so I understand that. The thing is that I got a bit confused because there is still always a control paradigm, right? So what I can rephrase from that is these controls that are out of the maybe natural way that you might control these embodied agents. because you mentioned the interfaces and all of these ways to control a swarm in that way. So I will position that more as a group control, right? But of course, you can view this in different ways. One is if you are delivering individual interactions, direct interactions, you can reach something similar depending on what you are controlling, right? For example, if you plan to move the swarm from one place to the other, ideally you have the slider or something that all the agents can move from this place to the other. But if you only deliver these individual interactions, you have to take one by one, right? And to put it there. And you might have issues if everyone has some sort of like algorithm that try to pulse others. So you have to try to do this several times and without any success. And in that sense, it might be complicated if we don't deliver this sort of control. But we can think about other ways to have this control in not much in much a separated way. I would say, I don't know how to name this, but in a metaphor in which we separate these things. So if I think about a more embodied approach, the same example of this moving everyone will be like, okay, I have literally an object here in the center, and I move in the center, and I move everyone. So then I can take away the slider paradigm and have this approach.
That's very interesting. And there also, I want to come back to the multi-agent systems and the first definitions that we first settled in, which is, an agent acts. In that case, if we approach the human agent acts, but that action is defined as control, right? Do we have to do that? Isn't there other ways to do that?
Do we have to do that?
Yeah.
But you mean like if something is happening, because like there could be the decision of like, okay, they are doing something, right?
Yeah.
And then we can observe the behavior. And if the behavior satisfy what I'm doing, so maybe we don't have to act.
For example, could the human be another agent of making sounds? That's sort of where I'm trying to get to.
Yeah, okay. Yeah, like the user as one of the agents. So actually, in the Swarmulator system, that's sort of the approach that I try to want to do. But in this case, giving a little bit more of power. Because you are this, in individual interaction, you have this cube, right? And this cube is like, you can move it as you please. And then you can influence the other. So you basically are one of these agents through this cube. But of course, like if we raise the complexity in terms of sound, and you want to interact with them in other ways, with other sensory capabilities of them, you can, for example, like play an instrument, play a sound, and they can literally listen the sound in some way, using machine listening or other kind of strategy. So in a sense, you can do it. It's an approach, like as user, as the agent. But of course, you might have some extra capabilities that might help to reach some goals depending on the design that you're doing.
I mean, this is a fantastic conversation. I would like continue this for quite long, but I won't for the sake of time. I have one last question.
Okay.
You mentioned the PQF plus K architecture, which is really interesting. If you think about it, and if you look into these like all new trendy approaches where we have large language models and such. But also if you go back and PQF plus K is maybe 2010s, if not earlier. So there's a perception module, which could be, something like, like a voice recognition or image recognition that we have right now. So that could be perception. And we have large language models, which could be the patterning approach. And then F is analysis, or, the output coming out of the patterning. And knowledge could be, for example, we have retrieval augmented generation sort of things where now you have a database that the patterning goes back to. So this is sort of almost like this has relevance to what's happening today. It's in a larger context, maybe, with much more advanced approaches, but the architecture is not so different. So my question to you is, from what you learned in your thesis, if you would like to inform, this kind of trend going on in the general AI research, what do you think your comment would be? What would you recommend to that?
Yeah, I would say like some sort of organization of these AI agents, like because like you have all of these generative models, these things that you can use and everything, but my perception is that it's sort of everything over the place. So if you can group this as a multi-agent system in a way in which everyone like try to communicate with each other to improve some task, you might have something interesting. And then you can like frame this into this PQF architecture. So instead of a swarm algorithm there, you have like a multi-agent system of these like complex agents. But the point is that, or the challenge is how can you communicate and how can you like establish this interaction between them so that you can have a better output or synthesis part according to what you are getting of that. Of course, in terms of architecture, this is one of probably many architectures that are there. And you can take different approaches. This is one that at least resonates with me and the approach that I was taking because also was used in the first music swarm systems. And I think that it's still valid in some way. But we can always like shape this and try to see what new approaches can help us to this organization of the agents. This is one that might help.
Thank you.
Okay.
All right, I want to thank Associate Professor Kevanch Tatar for his assistance. Does anyone want to speak ex auditorio? All right, then the committee will withdraw to evaluate the disputation. Then, yes. Then I ask you, Stefania, Serafin, has the committee found the disputation satisfactory?
Yes, absolutely.
Okay, applause. Then it is my pleasure to, on behalf of the Department of Informatics, congratulate you, Pedro, on this great achievement.
Okay, thank you very much.
Our report will now be made to the Faculty of Mathematics and Natural Sciences, confirming this. And I can now declare these proceedings concluded and invite all of you to come to the Rhythmo kitchen for a reception. Thank you.